Okay, so you can see on this left example that when we factor the top, it's a difference of squares technique, and the denominator is a different technique, not necessarily difference of squares. CPM generic rectangles can factor this either way. That we see that we have this x plus 2 term that cancels on the top and the bottom. And this right here indicates to us that there is a hole when x equals -2 versus a vertical asymptote. So we carry on to the next step. We still have the limit notation included, so we haven't done the limit yet of that simplified expression. And from here to there, we can see that x equals -2 is no longer a problem in that denominator, so we go ahead and plug it in with substitution. Simplify it to -4 over -3, which of course reduces to +4/3. So something to keep in mind here again is that limit notation didn't just go away because we didn't want to write it anymore. It actually is an operator that we have to carry through our process. Now on this example to the right, we have a cubic in the numerator, a linear in the denominator. Cubics get a little bit trickier to factor, especially in a case like this. This is a special case algebraically. So you can see to the left, I've started a CPM generic rectangle. Now we know that if we plug in x equals -1, we have a 0 in the denominator, which is a problem, but we can also sneakily plug that into the top and we realize it's also a 0 in the numerator. Well, that gives us a hint on how to do the division of this polynomial or set up the rectangle. So we know that when x equals when x equals -1, that divides the cubic evenly. So that means that x plus 1 is a factor, divides it evenly, of that numerator. So we can set up the generic rectangle as such. And then as the way they work, we can kind of do the puzzle game here. So you can see the x cubed and the 1 are already in there. So we're trying to figure out what is the other thing. If x plus 1 is a factor, what's the other thing being multiplied? So we say, well, we know that has to be true. And then this box is x squared. Now we know these two boxes right here have to cancel out to a no quadratic term because we don't have it in this numerator. So this needs to be -x squared, which makes right up here -x and makes this -x. Likewise, I don't have an x term in that original cubic numerator. So this also has to cancel out with that diagonal term. So we get that and finishes off our generic rectangle as such. So what that means is I can write this factored as x plus 1 times x squared minus x plus 1. That cubic in the numerator factors to that. Again, kind of a special cases, and we use the fact that we know -1 divided that numerator to get that. So this is all over x plus 1. All right, we see algebraically those two cancel out. Also, this tells us that, again, there is a hole when x equals -1 on this graph. We'll go down here, and we now have the limit. All right, so we now have no issues with plugging in x is -1 into that polynomial right there. So and we've got to be careful with our negatives and substituting in. So something to be on the lookout for. Again, notice I kept with the limit notation until this step right here where I actually substituted it in, and that gives us our limit of 3. Okay, on this example, again, we're evaluating this limit algebraically. The first thing we look for is there a problem with this x value? And the answer is yes. Our denominator, if we plug in x equals 0, we're going to get division of 0 in the denominator right there. Oh, it's a little heavy for highlighting. So our goal with these, and this is getting a little bit heavier with algebra because we got fractions within fractions, is if we're trying to do this algebraically, we want to get that division of 0 to no longer be a problem through algebra. So hopefully we can combine like terms, common denominators, stuff like that to make that x in the denominator no longer be an issue. So I'm going to go ahead and work this out a few times, then I'll come back and talk about each step. Oh my gosh, look at all this algebra. Yes, it's kind of a lengthy process, but guess what? We're heading into plenty of stuff just like this. So I've worked out steps kind of more so than I will in the future. We will streamline this process, but a couple of talking points starting with our first step, common denominators. So I'm multiplying to get the numerator of the top of this fraction with common denominators on both of those independent fractions. So we get this step right there, okay? And then again, we're out constantly asking, can I plug in x as 0? No, still got an x in that denominator right there. So we combine those two fractions to get this new numerator. Now, believe it or not, one of the big problems of this class is going to be this quantity right there. If you do not put a parentheses around that, that's going to burn several of us a couple of times this year if we don't get it figured out quickly. So that right there is a very important habit to start if you don't already have it. So anyway, combine those numerators, then we see we have some like terms after we distribute that negative symbol, and this is what many of you will forget. Not many, but a few of you will forget is that negative distributing to that secondary term in there. And then again, these twos cancel out to 0, and we finally start getting this thing a little more simple in this step. Okay, from here to there, I am just the very bottom denominator, I'm treating this division as multiplication of the reciprocal right there. Okay, so I turn that division into multiplication, and there we see that this x and this x cancel out, and I get this nice looking term right here, which now no longer has a problem for x to be 0. So we go ahead and plug it in. You notice my limit notation disappeared from this step to that step. So that tells you, or more importantly, you are telling me that you've taken that limit. And I just did that mental math in my head. So we get the limit of -1/4. Again, I encourage you to graph or put this function, the original fraction, in the grapher. And that's actually not a trivial thing to do. So that would be good practice for you putting kind of nastier looking things into your grapher. Put that in your y equals and then just check your tables and see if it seems like from both sides it looks like it's -1/4. Okay, on this next slide, we have theorem 1.8 in our book, which is the squeeze theorem, or also known as the sandwich theorem in other calculus texts. And basically, what everything in this blue box is saying is if we have a function f that is bound between two functions, it can be equal to them as well. And the limit of the upper and lower function are the same value at a point C. So it's talking about this x value of C, that the upper and the lower have the same limit. Then the function bound between the two has to also have that same limit. So kind of a interesting theorem when you think about this, and again the picture is like, well, yeah, that makes sense. So here's an example using the squeeze theorem. Okay, so if you take a look at this limit, we want to go as x approaches 0 of this x squared times the sine of 1 over x. So we can think about this first using the properties that we spoke of recently. I could rewrite that limit as the limit as x goes to 0 of x squared, and properties of limits say I can multiply that to the limit as x goes to 0 of sine of 1 over x. So we can break it apart like this, and now this is easier to think about. We know a lot about x squared, and we've learned recently about this thing right here. So x squared, we can go ahead and do a direct substitution because there's no problems with that parabola when x equals 0. So this limit right here is 0 multiplied by, if you recall this example from 1.2, I believe. This thing is that crazy oscillator. As we get closer and closer to 0, the sine function is just going back and forth harder and harder. So this limit does not exist. Now we have to be very careful here because we have an idea that we've been taught in mathematics that is not necessarily true here. 0 times anything is 0. Well, that doesn't quite work out here because of this concept. Okay, 0 times another number truly is 0, I believe that, but here we have to be careful. We're on kind of uncharted territory here of 0 times does not exist. What does that mean? And I also can't say this just doesn't exist because it might actually be 0. So using the property of limits that allowed me to do this multiplication gets us in kind of a crunch. We don't know any better than where we started. So we kind of hit a dead end with that property, and what I'm going to do is I'm going to use the range of, actually I just want to say, using the range of sine. So we hopefully know that the range of sine looks like this, and I'm leaving the angle open in this case, but you'd agree that our sine function is bound between the y values, the output values of -1 and +1. So it doesn't matter what angle I put inside this sine function, so I'm going to go ahead and write the thing of interest right there, the sine of 1 over x, and again, this is a true statement. Well, I can use algebra, and I can multiply all 3 parts of this compound inequality by x squared, giving us this new compound inequality. Okay, and what I'm doing here is I am forcing a relationship of the original limit right there. So I've now have that, and what we're doing here is we're bounding this function that we're kind of unsure about, this limit between 2 extremely familiar functions. Okay, so if we actually think about this graphically, we know a lot about this parabola, we know quite a bit about that parabola, and if we were to sketch these, let me go up here. We know the x squared parabola looks like that. We know the negative x squared parabola looks like that. And what we're saying is, or what this thing is saying is, that thing, that function lives somewhere in between these two. Okay, so I don't know what it's doing exactly, but we get something like that possibly. It's a sine, so I'm assuming it's oscillating. It's definitely oscillating. Okay, so what we now have is we can actually use this squeeze theorem, and we'll say this. I'm going to pause the video and write out my statements here. We get to say that because we know the limit of negative x squared is equal to 0, which is also the limit of positive x squared, that the limit of this thing as x approaches 0 also has to be 0 because it is stuck in between those 2 functions according to this relationship over there. It's bound between them, or it can be less than, greater than, or equal to those upper and lower bound functions, but because they both point to 0, when x is going to 0, then the squeeze theorem can show us this interesting fact. So just to go back and recheck in with our objectives, applying the squeeze theorem, that's where we ended off, using that interesting x squared, the limit as x goes to 0 of x squared times sine of 1 over x, finding limits algebraically and using direct substitution. We saw some difference of squares techniques, general factoring, and kind of getting creative with the CPM rectangle. And then of course we started earlier with the properties of limits that showed us that we can multiply the product of 2 limits